Now, before we launch into talking about probability, it's necessary that we have some common language here, so let's get some vocab down first. Now, I want to be able to talk about a trial, and all a trial is a procedure with a well-defined set of possible results. An outcome is the result of a trial. An event, one or more outcomes, and the probability, the likelihood that that actually occurs. Now, it can be kind of abstract like this, so let's look at an example. Let's say I wanted to find out how many years someone has attended Loyola. Now, my trial would be asking someone this. So, trial would be asking someone, how many years have you been at Loyola? The outcomes would be, they could say, well, I've been here no years. I might have been here 1 year. May have been here 2, 3, 4. Maybe someone's actually been here 5 years. So these would be our possible outcomes. That is the possible results people give us. Now, if I put little braces around this here, it's a list of all possible outcomes, and this is what we call a sample space. So sample space is a list of all the different possible outcomes. Now, when we talk about an event, we're talking about one or more possible outcomes. So, for instance, in this case, one possible event might be someone has been here under 2 years. We call this an event because it includes, once again, one or more possible outcomes. If I say you've been here under 2 years, that could mean you've been here 0 years, or maybe you've been here 1 year. Now, the probability would be the likelihood that this happens. So, for instance, if I want to look at the probability, someone has been here 1 year. Or I could look at been here under 2 years. So once again, this would just measure the likelihood that this would actually happen. Now, when we look at the probability of something, we have some nice notation for it. And so in general, if I want to write the probability of something, I would write that the probability of A for whatever event A is. So for instance, if I want to find the probability someone has been here 1 year, I would write the probability of 1 year. Now that we've got some common vocabulary, it's time to go ahead and talk about notation. Now, I've already introduced the idea of just straight up probability notation. And that is, if I want to talk about the probability of an event A, I can write that as P of A. Now, aside from the just very basic probability notation, we can also make it a little bit more complicated. And that is, if I want the probability of A or B, I can write this as a probability of A or B. I can also write it as the probability of A union B. And once again, that little U right there is read as union. A good example of this would be if I want to write the probability someone is either a nursing major or a pre-med major. This includes all the people who are nursing as well as all the people who are pre-med majors in this probability. After or probabilities, we're also going to be talking about and probabilities. So the probability of A and B can be written as the probability of A and B. I know that's not surprising. As well as the probability of A intersect B. So this is an intersection. We'll be talking more about why we use a union versus an intersection for or versus and later on. For now, though, I just wanted to go ahead and introduce you guys to the different types of probability notation we're going to be dealing with. Now that we have common language and notation, it's time to actually introduce the idea of probability. In general, we're always going to understand the probability of A to be between 0 and 1. Traditionally, we write probabilities as decimals or as proportions. We'll also talk about them as percentage, but we'll default back to this proportion idea. So for instance, if I write, what's the probability I get a heads when I flip a coin one time, we have this common understanding that's about 50%, or 1 in 2. Now, when I write that, I can write as 1 over 2, I can write as 0.5, I can also write as 50%. We're going to try to always default back to that 0.5 there. Now, flipping a coin once and having a 50% chance of getting heads makes a lot of sense, but let's talk about what if I flip the coin more than once. So, for instance, if I flip a coin 2 times, and I want to go ahead and understand, well, what are the chances I get a heads? What are the chances I get a tails? Then what I can do is I can actually go ahead and list out my different options. That is, I know if I flip a coin 2 times, there's a chance I get heads. Maybe I get heads and tails. Maybe I get tails and heads. And maybe I get 2 tails. If I go ahead and put little braces around this, remember this is called a sample space. And it allows me to list all my different possible options. Now, each of these options are actually equally likely, which makes this really straightforward to do. That is, if I want the probability I flip a coin 2 times and I get heads both times, well, there's only one option that gives me that, so it'd be 1 over the 4 total options in the sample space. So that is 1 over 4. Now, once again, this only works because each of these options are equally likely, but it's helpful. So, in the case where I have equally likely possible outcomes, I can calculate the probability of A by taking the number of outcomes in A and dividing it by the number of outcomes in the sample space. So, for instance, if I wanted to know what is the probability I get 1 heads out of flipping a coin 2 times, I could go ahead and count it up. Now, I want outcomes that have at least 1 heads. Sorry, not at least, exactly 1 heads. So when I look at this outcome here has 1 heads, and this outcome here has 1 heads. That tells me then that I have 2 possible outcomes that have 1 heads out of a total of 4 outcomes in my sample space. This means I have half, or 0.5. So there's a 50% chance that if I flip a coin twice, I get exactly 1 heads there somehow. Let's do one more just to make sure we're understanding it here. I want to know what's the probability I get no tails. So go ahead and pause the video, see if you can figure out, and then come back to it. Now, I'm hoping here that we have 4 total options, and in reality, when I look at it, there's only one option that has no tails, and that is this one here that's heads. So, I have 1 out of 4, or 0.25, or 25% chance of getting absolutely no tails in there. Now, this goes ahead and introduces us to another concept, which is, okay, so no tails versus having at least 1 tails, and that's what we'll be talking about in the next video. In order to explore the idea of complements, we first need to understand what it means for 2 things to be disjoint. Now, in general, 2 events are disjoint if they share no possible outcomes. So, for instance, I would say being a nursing major and being not a nursing major are 2 disjoint events. They're disjoint because if you're over here, that means you are not over here. You are one or the other. So this is disjoint. It means the 2 don't occur at the same time. Now, the thing with 2 disjoint things is they don't necessarily make up all the possible options. For instance, being 10 and being 11 years old are 2 events that are actually disjoint. That is, you can't be 10 and be 11 at the same time. But it's not like you're 10 or 11. There are other options out there as well. So here I have being 10, being 11, or other. 3 different things that are disjoint. I want to emphasize once again that just because 2 things are disjoint, like being 11 and being 10, doesn't mean they make up all possible options. Now, there are going to be the case where we have 2 things that are disjoint and they do make up all the possible options. This is called complements. And in general, the complement of A is made up of all events that remain if A is removed. So, for instance, if I say you're a cat person or not a cat person, it is one or the other. That is, all the people we have either fit into this category or this category right here. These 2 are what we call complements. If I call this A, this is the complement of A. Now we have notation for this as well. If I call that A and this is the complement of A, I can represent that by putting little a with a C on the top of it. So let's go ahead and try a couple different examples. Okay, so if I say someone goes to Loyola, I want you to think about what the complement of that would be. That is, if this is A complement would be does not go to Loyola. That is, when we're talking about complements, we're really just talking about this whole idea of having an opposite. Now, these examples are pretty straightforward, so let's make it a little bit more complicated here. In the previous videos, we talked about having a heads versus a tails. So, if I say there are no heads when I flip a coin 2 times, the complement of this would be, okay, you could have 1 head, you could have 2, you could have 3. So the complement of no heads would be at least 1 heads. So once again, no heads would be having 0 heads. But I could also have 1, 2, 3, 4, and for that reason, the complement of having no heads is at least 1 head. To really see this, let's go ahead and list that sample space again. The sample space for flipping a coin 2 times was heads, 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 tails, tails, heads, and tails, tails. Now, if I'm looking at the idea of having no heads here, that includes any of these events that don't have any heads in them, which would be just this one right here, tails, tails. The complement of that would be everything else. So the complement would be all of these. And once again, complement's just everything that's left after I remove that thing. So if the complement of no heads includes all of these 3, notice it includes heads, 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 tails, tails, heads. And what these ones have in common is that they have at least 1 heads. So in summary here, we talked about the fact that 2 things are disjoint if they have no overlap. Cat person, not cat person. Being 11 years old, being 10 years old. Those are disjoint. The complement is more specific. Not only are complements opposites, but they have to incorporate all the possible different options. That is, with complements, you either fit into one or the other. There's no in between with it. So disjoint, no overlap. Complements, no overlap, and they take up all possible options. So to understand how complements are going to help us here, let's go ahead and look at an example. Now, in mid-2018, a poll by Gallup found that 36.8% of the citizens in allied nations approved of U.S. leadership. Now, I can rate this by saying the probability someone approved was 36.8%, or 0.368 as a decimal. Now, let's say I wanted to find the probability of the complement. That is, if I have approved, the only other option is that they did not approve. So I have approved versus its complement. I'm going to go ahead and write an A up here and an AC here to represent complement. Now, if 36.8% approved, I need to find the percent that don't approve. I know in total there are 100% of people, right? And so if I take the 100 and I subtract off the 36.8% that approved, I'll be left with the percentage who didn't approve. And that in this case, I believe, is 63.2%. That is, if I take the full 100%, subtract off those who approved, I'll get those who do not approve. This gives us our first formula here. And that is, in general, if I take 100% minus the percentage of one, I get the percentage of the other. I'm going to write this as a decimal instead. So I know 100% is 1 as a decimal. And if I take 1 minus the probability of A, I get the probability of the complement. So once again, if I take 1 minus 0.368, I'd get 0.632 out. So this is our first little formula here. And it tells us once again that if I want the probability of the complement, I take 1 minus the probability of the original, and it'll give me the complement out.